So this is again back to non-singularity. Okay, so if you recall that if P is a point in X which is an affine variety, okay, then it is an affine variety in say An, okay, then P is called non-singular, called a non-singular point of X, okay, or we say X is non-singular at P, okay, we say X is non-singular at P if for a given set of generators for, let me not say let me even say for some given set of generators F1 etc. Fl of the ideal of X, okay, the rank of the Jacobian matrix of F1 etc. Fl with respect to the variables x1 etc. xn at the point P is equal to codimension of X, which is actually, which means dimension of the affine space, the ambient space minus the dimension of X, which means it is n minus dimension of X, okay. So this was the definition of a non-singular point. A point of an affine variety is called a non-singular point or a smooth point, or we say that the variety is non-singular at that point, okay, if for some given set of generators for the ideal of the variety, if you calculate this Jacobian which is given by the partial derivatives of all these with respect to these variables, that turns out to be the codimension of, that turns out to be equal to the codimension of X, okay, and codimension is the dimension of X taken away from the bigger space in which X sits, which is affine space, okay. So and of course this so you know this is just dou f j by dou xi at p, it is just this matrix, okay, and where of course the xi's are all affine coordinates of an. So x1 etc xn, if you take, they are coordinates on an, okay. So this is the definition of non-singularity, and then you know this generalizes, this can be used to generalize to say when a point on any variety is a non-singular point, and the definition will be that, well, given any point on any variety, it always lies in an open set which is an affine variety, because any variety is covered by a finite union of open subsets which are isomorphic to affine varieties. So you take the point on the variety to also to be a point on an affine open set containing that variety, and then you define the point to be non-singular if it is non-singular as a point of that affine open set, okay. And so in a way, you know, this non-singularity should not depend on the open set in which you are considering it. So it should, so you know, the non-singularity or the smoothness at a point is a very it's a local notion, okay. You know, when you say a curve is smooth at a point, it means actually there is a sufficiently small neighborhood of the point where it is smooth, okay. And similarly, you know, when you say a surface is smooth at a point, it means there is a sufficiently small neighborhood of the surface where it has to be smooth. So you see, the smoothness at a point is something that is it's not, in fact in classical geometry, you know, if something is smooth at a point, then it is also smooth in a neighborhood of that point, okay. And this is true also in algebraic geometry, okay, but it requires more commutative algebra, it requires more algebra to establish, okay. The fact is that something being smooth at a point is something that spreads out to that neighborhood of the point, alright. Therefore so the moral of the story is that when you say x is non-singular at a point, it will happen not only at that point but also in an open set containing that point, alright, in a neighborhood of that point. And in that sense, you know that, but you know, any open set in the Zariski topology is huge, okay. Therefore what it will tell you is that the moment you have one smooth point, okay, then there is a huge open set, there is a dense open set full of smooth points, okay. And this is what happens in truth. What happens is that the set of points which are singular points which are not non-singular, that is only a small closed set, okay. And that means most of the points on an all points on a huge open set, they are all non-singular, they are all smooth points, okay. But anyway, these are all geometric facts, and one needs to have sufficient amount of commutative algebra to establish them, alright. So at the level of this definition itself, there are problems in the sense that, you know, this variety x could sit in some other affine space, and if I change the affine space, then the ideal of x in the affine space will change, okay. And not only so, that's one ambiguity, and the other ambiguity is, for this ideal I am taking some set of generators. If I take another set of generators, then it may be different number of generators and this matrix changes, but I am just saying that so this is a condition on the rank of this matrix, okay. So there are a lot of ambiguities in this definition. Why should this definition be a good definition? Because there are so many choices to be made. First of all, I have to make a choice of embedding x into some affine space, namely I have to think of x as an irreducible closed subset of some affine space, okay. And variety can be embedded in so many ways, okay. I can think of, if the variety is a line, of course I can think of it as a line in the plane or a line in the space, in 3 space or even higher dimensional space. So there is this ambiguity in embedding it in some an, and then once you embed it, if you look at the ideal of x for that embedding, that ideal of course already depends on the embedding, but then it could have different sets of generators, okay. The same ideal could have different sets of generators, and they could and the number of generators in these sets could also be different, okay. Therefore this Jacobian matrix which is a Jacobian of all these generators, this matrix itself could change, okay. But then the definition is that whatever it is you calculate its rank, if its rank is equal to codimension, then the point is a smooth point, a non-singular point. So it looks like this definition involves too many ambiguous things, and it might not be very consistent if you change the choices, the various choices, but that is not true. The point is because this has got to do with the this has got to do geometrically with trying to look at the tangent space to the variety x at that point, okay. And that is the reason, it is because of that geometric reason that this definition actually works. But then if you want to really verify that, one uses of course you translate from geometry into commutative algebra, and the necessary commutative algebra is given by the following theorem. So here is the theorem. The theorem is that a point P of x where a point P of a variety x is non-singular if and only if the dimension of MP by MP squared over K is a K vector space is equal to the dimension of OXX which is equal to dimension of x, okay. So here is the this is the theorem, alright, where of course where MP inside OXX is the unique maximal ideal. Okay. So this is basically this is due to Zariski, Oskar Zariski, and it is a fundamental result. And here that the definition of non-singularity we are using is this definition, which is full of ambiguities, okay. This definition is full of ambiguities, alright, and whereas this theorem gives a condition, the condition is only on the local ring of the variety at that point, and you can see immediately one thing, because it is a condition on the local ring, I can assume that this point is on an affine variety, because I can go to an affine open subset of this variety and look which contains the given point, okay. So it really does not, so it depends only on the local ring, alright. And if I, and the beautiful thing is that this is intrinsic to the variety. See here nobody is bothered about whether x is affine or quasi affine, or if it is affine or quasi affine, which affine space it is embedded inside. I mean all these things one is not bothered about. The condition is completely in terms of things which are intrinsic to the variety, okay, and which do not depend on the variety being seen as a subset, either irreducible closed or open subset of an irreducible closed in some affine space or some projective space. Nobody is bothered about these things, okay. So that is the reason why this theorem is very, very important. And so so the proof is interestingly, the proof is linear algebra, and but actually it has got to do with geometry, because what you are trying to do is you are actually if you look at it geometrically you are trying to calculate the tangent space at the for the variety at that point, okay, and you are also trying to look at the normal space, okay, the space of vectors in the ambient space, ambient tangent, the tangent space at that point for the ambient object, and you are looking at the normal directions also, okay. So so the idea is that yeah, oh yeah, okay, yeah, that is very important, yeah, it should, thank you, it should be OXP, because all the time I am used to small x and then yeah, that is bad notation, thank you. So this should be OXP, this should be OXP, not small x, right. So so you know the roughly geometrically this is what is happening. What happens is that when you think of an object embedded inside a space, okay, then you take a point on that object, okay, then it will have a tangent space, okay, and then the normal space will be the normal vectors in the bigger space, and the sum will add up to the dimension of the bigger space provided the point is smooth, okay. So you know if I take a smooth surface in 3 space, if I take a smooth surface in 3 space, take a point on it and draw the tangent space, I will get a tangent plane, I will get a neat plane, 2-dimensional plane, and I will get a unique normal to the surface which is given by the gradient, okay. If the surface is defined by a single equation, it will be given by the gradient, and then therefore the normal space will be 1-dimensional, the tangent space will be 2-dimensional, sum of these spaces will be 3 dimensions, which will be the ambient space in which the object is embedded. But however, if you take a singular point, this will not happen. The singular point, the tangent space itself may be everything, you may not have any normal vectors. For example, if you take the cone in 3 space and you take the vertex of the cone, which is a non-smooth point, if you draw the tangent space, then you will get the whole 3 space. So you will not be able to find at the vertex there are no normal vectors, all vectors are tangent vectors, there are no normal vectors. So this kind of, so if you you see that this happens because that point is a singular point, okay. So if you have a smooth point, what will happen is that you will get a tangent space at that point which is equal to the dimension of the object, and then the normal space which consists of vectors perpendicular to the tangent vectors, okay, that will give you a subspace of the tangent space of the point in the bigger space in which it is sitting, okay, such that the sum of these 2 spaces will be the whole tangent space, okay, and this will happen for smooth points, it will not happen for non-smooth points, okay. And actually it is that calculation which is being reflected here, but it is being reflected using algebra, alright. So what you will do, so let us do the following thing. So without loss of generality, we assume x is affine, okay, and why is this correct? This is correct because after all my definition of non-singularity is a point P of a variety is called non-singular if you it is non-singular as a point of an open subset which is affine, because I have defined non-singularity only for a point of an affine variety, and any variety can be covered by affine varieties, open subsets which are affine varieties. So without loss of generality I can assume that x is affine, alright, and that means and what I mean by this is you go to an open subset which is affine, okay, by going to an open affine subset containing the point P, okay, and you know by going to an affine open set which contains the point P, the local ring is not going to be changed, because the local ring does not depend on whether you go to a smaller open set which contains the point or not, okay. So the conditions of the theorem are both the hypothesis and conclusions for the theorem, both ways of the theorem, they are not affected if you go to an affine open subset, okay. So it is enough to go to consider x affine, okay. So say we are in this situation, P is a point of x which is inside affine n space, and now it's affine variety means it's an irreducible closed subset of an, alright, and then you know now we will do some calculations. Okay, so now first of all let P be the point lambda 1 etc. lambda n. Okay, P is a point of n space anyway, so take its coordinates. Okay, so the maximal ideal of P will be by the Null-Stellen-Satz, I mean the point P corresponds to a unique maximal ideal in the affine coordinate ring of the affine space, which is k x1 through xn. This is the affine coordinate ring of An, alright, and here I will get a maximal ideal which corresponds to this point by the Null-Stellen-Satz, that will be this maximal ideal generated by the xi minus lambda I. Okay, so this is the maximal ideal that corresponds to this point, alright, and you see what we will do is, see you define this map k x1 through xn, you define this map psi, okay, into kn. So here is my map. The map is very simple. Take any polynomial g in n variables, simply apply, I mean take its gradient, just take the gradient at p, okay, which means take dou g by dou x1 at p, dou g by dou xn at p, just do this. So just take the partial derivatives with respect to each of the variables in this order and then evaluate them at p. Okay, so of course here when I say partial derivative, it is a derivative that is in the formal sense, you know how to write the derivative of a polynomial without having to get the derivative from calculus methods which involve epsilons and deltas and limiting processes. Okay, so we just use the standard rules for differentiation, formal rules for differentiation of variable, and you write out these. So each of these dou g by dou xi's are all polynomials again in the xi's, and then you just substitute the point p, namely you substitute instead of each xi you substitute lambda I, you will get some n tuple, and that is this n tuple of kn. Okay, now the point about this map psi is, nice thing about this map psi is that it is k-linear and surjective. Okay, see the map psi is k-linear because if instead of g, if I replace g by g1 plus g2, okay, then all the partial differential operators, they are all k-linear, I mean they are all linear, and therefore if I replace g by g1 plus g2 I will get a sum of tuples here, and if I multiply this g by a constant, that constant will come out there. Okay, therefore it is k-linear, and it is surjective because if you take if you see if you take these generators of the maximal ideal, okay, if I take x1 minus lambda 1, alright, for g, then I will get 1 0 0 0 0, which is the first basis vector. Okay, because if I differentiate this with respect to dou with x1 I will get 1, and substituting p has no effect, it will still remain 1. If I differentiate with respect to other variables I will get 0. So if I take g equal to x1 minus lambda 1 I will get 1 0 0 0. If I take x2 minus lambda 2 instead of g I will get 0 1 0 etc. So in this way I will get a basis for kn, okay, and since the image contains a basis it is surjective. Okay, so the moral of the story is that psi is k-linear surjective psi of xj minus lambda j is equal to standard jth basis vector. Okay, so so it is a linear surjective map, alright, and now the point is that the kernel is exactly the square of this maximal ideal. Okay, so in other words what I am saying is that psi induces an isomorphism of the n dimensional vector space k with m mod mp mod mp squared. Okay, so mp mod mp squared is just the n dimensional vector space k. So you see if we take an element of MP squared, okay, then it is of the form it is going to be of the form sigma I some gi times xi. So I know in fact I can put I comma j xi minus lambda I, so I put gij xi minus lambda I into xj minus lambda j. Yeah, that's right. Okay, you see what is an element of the square of an ideal? It is a finite sum of products. It's a finite sum of products where each term in the product is a product of two terms, one each from the ideal. Okay, so if I take an element of MP square, it's a finite sum where each term has to be an element of this ideal, but any element of this ideal will be generated by the xi minus lambda I with polynomial coefficients. So it will look like this, alright. And now the point is to this, if I apply the operator dou by dou xl, okay, suppose I apply the operator dou by dou xl, alright, then what will I get? You see if L is so I have to differentiate the product of three terms, alright, and therefore you use the product rule, alright, which also is valid in this case, okay, formally, alright. Therefore see if L equal to I, suppose L is I, then what I will get is I will get so let me write it here. So what I will get is well, sigma I comma j, I will get dou gij by dou xl at p, and then I apply p. Okay, so this is this is the Lth component of this map psi. The map psi is apply all the operators, all the partial differential operators, and then substitute the point p. So the Lth component of this map, that is this map followed by Lth projection, that is this map, alright. And what is it? If you apply the chain rule, this is this will be xi minus lambda I xj minus lambda j at p, alright. This is one term, then the other term will it will have gij at p, and then I will have dou by dou xl of xi minus lambda I into at p into xj minus lambda j at p, and then I will have one more term I will have xi minus lambda I at p into dou by dou xl of xj minus lambda j at p. Okay, this is what I will get, alright. And now if you look at it carefully, this is going to vanish, because you see the first term will vanish because I have these two fellows surviving. If this is 0, then I am not worried, okay. But even if this is not 0, if I substitute xi equal to lambda I or xj, when I substitute p, I have to put xi equal to lambda I and xj equal to lambda j. So this is gone. In this, this will go, and in this will go. So these terms will vanish, these underlying terms. So this is actually 0, okay. So the moral of the story is that if you take any element of MP squared, this linear map will kill it, okay. So in other words, what it will tell you is that MP squared is contained in the kernel of psi, okay, MP squared is contained in the kernel of psi, but the more important thing is MP squared is exactly equal to the kernel of psi, okay. Conversely, let H belonging to MP be in kernel of psi, okay. Now H is an element of MP, so H is actually given by sigma gi xi minus lambda I over I. This is how an element of M, the maximal ideal, will look like. It is just a combination of all the generators xi minus lambda i's multiplied by polynomial coefficients. The gi's are polynomial coefficients, right. This is how maybe okay, this is gi and this is gij, so it should not, they are different things, right. So H looks like this, alright, and I am saying that I have taken my H to be in the kernel of psi, so psi of H is 0, okay. So psi of H, but what is psi of H? Psi of H is, well, I have to apply dou by I have to partially differentiate this with respect to each variable and then substitute the point P, then I should get 0, that is what it means to say that psi of H is 0, which is H is in the kernel of psi, okay. I am trying to show that kernel psi is also contained in MP squared, so I am trying to show kernel psi is equal to MP squared, that is what I am trying to show, okay. So psi of H is what? If I differentiate this with respect to if I take psi of H equal to 0, so this will tell you that, you know, if I take dou H by dou XL at P is 0 for all L, this is what it means, okay. And now write that out, see dou H by dou XL at P 0 is equal to this, but what is, see, if I differentiate this I will get sigma over I, okay, I will get dou gi by dou XL at P into xi minus lambda I at P plus I will get gi at P into dou by dou XL of xi minus lambda I at P. This is what I will get, okay. And what you must understand is that you see this is good, this is 0, xi, whenever xi minus lambda I comes, if I substitute the point P, it is going to vanish, okay. So this term is gone, alright. And this term, if you look at it, if L is not equal to I, this is 0, so this term will be killed, and this term will only survive when L is equal to I. When L equal to I, this is 1, okay, and I will get gi of P. So this crazy thing will tell you that GL of P is 0 for all L. This happens for every L. So GL of P is 0, but that means what? It means that the GL, see, if a polynomial vanishes at P, then it is precisely in the maximal ideal of P, because MP is exactly the ideal of polynomials which vanish at P. So what this will tell you is that it will just tell you that you know GL is in MP, okay. But you know if GL, and that is for all L, so you know all these GIs are in the maximal ideal and these terms are also in the maximal ideal, therefore the product is in M squared and therefore H is in M squared. So this implies that H is equal to sigma gi into xi minus lambda I is in MP squared. So all these things put together tell you that MP squared is exactly the kernel of psi, okay. Why take H in M? No, if H is not in MP I cannot write it in this form, it has to be generated by the generators of MP. so you can write H in this H is in this form if and only if it is in MP, because xi minus lambda I are the generators of MP. A general H need not be like that. Any polynomial need not be like that. What I forgot to tell you is that you see this psi is from this polynomial ring into this. Mind you, every ideal is also a K subspace. Okay, so this psi, the psi also gives you a linear map when restricted to a subspace. So psi can also be restricted to MP, and so in fact what I want to say is that psi restricted to MP itself is also K linear and surjective. Okay, so I'll come to that. So you know, note that MP squared is a subspace, it's a K subspace of MP, which is also a K subspace. Subspace means vector subspace, and there is this map psi into Kn. Okay, and in fact you see psi restricted to MP is also surjective, because you know I have already told you that psi takes all the generators of MP into the standard basis. So psi restricted to MP is also surjective. Okay, so psi restricted to MP from MP to Kn. Okay, so here of course I am looking at as you said, because I am taking H in MP, I am looking at the kernel of psi restricted to MP, right. So if you take psi restricted to MP has induces is surjective, and induces, I mean it's surjective because the generators of MP give their images under psi give you the standard basis, right, and it induces a K linear isomorphism from MP mod MP squared to Kn, and let me call this isomorphism as psi prime. Okay, so you know the first this simple linear algebra in this first step gives the calculation that you know you take a point P in affine space, okay, take the maximal ideal corresponding to the point, then MP mod MP squared is just n dimensional affine space. Okay, that is the calculation, alright, and you know if you look at it, in fact in view of in retrospect, you know, in view of the theorem that we are going to prove, what you are saying is that every point of affine space is non-singular. Okay, because you know if you take the local ring of affine space at that point is just the polynomial ring localized at MP, okay, and its maximal ideal is generated by the image of MP in that localization. And if you take, and what you are saying is that, well, if you take this quotient and localize, okay, you will get MP mod MP squared at the local ring, okay, for the point in affine space, and you are saying that the dimension of that is equal to the dimension of affine space, which is n. So you know if you take x equal to an, you have got this condition, and what you are saying according to the theorem is that every affine space is smooth. Okay, so the significance of this calculation is that affine space is smooth, is non-singular, every point of affine space is non-singular. Okay, the affine spaces are smooth, right. So well, anyway, I need to go down to this this subset. Okay, so well, see, for that I do the following thing. You see, you have see P is in X, and that is the same as saying that Ix is contained in MP. Okay, this is again you know this is just applying the the script I and the z functors to p and x, right, and using the Nordström ansatz. So you know p, see p is in x, so you are saying the subset p is subset of x, okay. You apply I to this, so you will get I of the point p contains I of x, okay, but what is the ideal of the point? The ideal of the point is exactly MP, so MP contains Ix, okay. So this is just applying the functor, I mean it is gotten by applying the getting the ideal of a subset, okay, and of course the ideal of point is maximal ideal, okay, MP. And so you know what will happen is that if you take Ix, so Ix is inside MP, right, and in fact if you take Ix plus MP squared, okay, that will also be a sub of MP, okay, because MP squared is a subspace of MP, Ix is also a sub of MP, the sum of two subspaces is again a subspace, alright, and in fact I can even divide now by MP squared, so I divide by MP squared and I get this is a subspace, it is a subspace of this K vector space which is isomorphic by psi prime to Kn, okay, alright. And the beautiful thing is if I take the image of psi prime and image of this under psi prime, you know what I will get, what is the dimension, of course psi prime is an isomorphism and this is a subspace, so the image of this subspace under psi prime will be a subspace of Kn, okay, and that subspace, what is the dimension of the subspace, what is the dimension of the image of a linear map, it simply you take you simply take a set of generators for the subspace, okay, and apply the linear map. The image of a subspace is just given by taking the span of the images of the generators of the subspace, okay. So if I want to take the if I take the image of, if I want the image of this, I have to just take a set of generators for this, apply psi prime to that and take the span of that, okay. In other words, of course instead of taking span of a set of vectors, you can write those vectors in column form, take the matrix and take the rank of that matrix, because you know the rank of the matrix will give you the dimension of the image, okay. This is the standard rank and nullity theorem in linear algebra, so it is part of that theorem. So you know, but you see now you know for Ix, if I take a set of generators f1 through fl of Ix, okay, then those generators will also give me generators here, okay, and applying psi prime is actually calculating this this Jacobian matrix, because actually what is happening is when you apply to each generator, okay, what you are doing is you are taking you are going to get one row or one column of that depending on the way you write it of the Jacobian matrix. So if you take the images of all these generators, I am just going to get the Jacobian matrix, and its rank is precisely going to be the image of this, okay, that is the connection. So moral of the story is dimension over K of Ix plus MP squared by MP squared is equal to dimension over K of psi prime applied to that Ix plus MP squared over MP squared, okay, and this is equal to rank of the Jacobian of dou f I by dou xj at p, okay, where f1 f2 etc. up to fl are a set of generators for the ideal of x as here, right. So this is how the you see now if you look at it like this, it is very clear that no matter what set of generators I use, instead of using f1 through fl, suppose I use some g, some h1 through h l prime, another set of generators, no matter how many generators they are, I do not care, okay. But in any case I am only going to get dimension of this subspace, and that is the reason why the rank of this Jacobian does not depend on what your generators are, okay. You are always going to get only dimension of this subspace, okay. That is the reason why even for a fixed embedding, for the ideal of the variety in the affine variety in the embedding into affine space, even if you change the set of generators, you are going to, when you calculate the rank of the Jacobian of the generators with respect to the variables, you are going to get only the same dimension. I mean you are going to get only the same rank, because this is a dimension of one and only one subspace, this subspace under this isomorphism, okay, fine. So alright, now it is a matter of just a little bit more of linear algebra, alright. So what you do is, so let me keep this statement here as it is and continue here, okay. It is only probably a couple of lines more. So what will happen is you have see, what you should remember is, you see MP mod MP squared divided by Ix plus MP squared mod MP squared, okay. I have this is a space and this is a subspace. If I take the quotient, my claim is that this is the same as MP mod MP squared, where this MP is the unique maximal ideal in the local ring of X at P. Alright, so you see we have an isomorphism of k vector spaces in this way, okay, because how do you get the local ring? You get the local ring because the local ring of X at P is gotten how? What you do is you take the affine coordinate ring of X and you localize it at the maximal ideal that corresponds to the point P inside X. No, this is the definition of the local, this is how you get the local ring of an affine variety at a point. You simply take the affine coordinate ring of the variety and you localize at the maximal ideal that corresponds to that point, the unique maximal ideal of the affine coordinate ring which corresponds to that point by the Nullstellensatz, okay. But what is Ax? It is just polynomial ring, you go modulo the ideal Ix, and then what is this maximal ideal? This is just MP, you localize at MP mod Ix, alright, and because of this, if you take this quotient MP mod MP squared Ix plus MP squared mod MP squared, this will be the same as small mp, where small mp is the unique maximal ideal in this, because you see small mp is actually this, you take the ideal mpx dot take the ideal generated by this, by its image in OXP, okay. So this quotient is the same as this, alright, as k vector spaces, and therefore if you count dimensions, dimension of this minus dimension of this is equal to dimension of this. So you will get dimension of mp mod mp squared over k is equal to dimension of capital MP mod mp squared over k minus dimension of Ix plus mp squared by mp squared, okay, right, and but you know, so that will be equal to, what is this? This is n dimensional, because we have already proved mp mod mp squared is isomorphic to capital MP by capital MP squared is isomorphic to Kn as vector spaces. Therefore its dimension, because of the isomorphism psi prime, its dimension is n. So you see this is n, okay, minus this part is just the rank of the Jacobian matrix at P. So this as we have seen here is the dimension of Ix plus MP capital MP squared by capital MP squared is actually the image under psi prime, dimension of the image under psi prime of that subspace, okay, and that is the rank of the Jacobian. So I will get n minus, here I will get n minus rank of the Jacobian of dou Fi by dou xj at P. I will get this, okay, and what is and this is equal to n minus dimension of x if and only if P of in as a point of x is non-singular. That is our definition of non-singularity. The definition of non-singularity is that the rank of the Jacobian should be equal to the codimension for a point which is a smooth point, a point which is a non-singular point. So this is equal to n minus of dimension of x, which is equal to dimension of x if and only if the point P is non-singular. So that proves the theorem. So what you have proved is dimension of m mod m squared, mp mod mp squared, where mp is the local ring, mp is unique maximal and ideal in the local ring corresponding to the point P on the variety x. That is equal to the dimension of x if and only if the point P is a smooth point, okay, and the importance of that is that this gives the tangent space at the point. This gives you the dimension of the tangent space at that m mod m squared, okay, dimension of m mod m squared, that actually gives you the tangent space at the point, okay, and therefore you are saying a point is a smooth point if and only if the dimension of the tangent space is equal to the dimension of the variety on which it lies, okay. In general what will happen is the dimension, if it is not a smooth point, this dimension can go bigger, you can get more tangent vectors, your tangent space can become bigger. If your tangent space becomes bigger, then if you calculate the rank of this Jacobian, that will become smaller, okay, and the point will be a non-singular point, I mean the point will become a singular point, okay. So the moral of the story is that this gives you the tangent space, okay, and this actually calculates the normal space. This is a set of normal directions at that point in the ambient space in which this space is this object is sitting inside, okay. So if the point is a smooth point and the x is an r dimensional variety in n dimensional space, then the dimension of the tangent space will be exactly r. The dimension of the normal space, all the vectors which are perpendicular to the tangent space, tangent vectors, that will be n minus r, and that should be equal to the rank of the Jacobian for any set of generators, and that is what geometrically is happening and that is what it says, okay. So that finishes the proof of this theorem. So so in this connection I need to tell you that the set of points where the set of singular points, that is a closed subset, okay. So that is also a fact that can be seen immediately from this argument. If you look at all those points where you have which are singular points, see those are points on the variety where this rank falls, rank of this matrix falls, okay. And you know where the rank of a matrix falls is just the rank is just given by the locus of the vanishing of the of all the minors, okay, of all the maximal minors, right. So if you have if you take this Jacobian matrix, okay, it is a matrix having polynomial entries, alright, and you know if you vary the point P, what are the points P which are singular? Those are the points for which if you evaluate the Jacobian matrix, you are going to get rank less than, you will not get rank n minus r, okay, but you will get lesser rank, okay. And what does that correspond to? That corresponds to you take all the maximal minors, square minors of the matrix, their determinants should vanish. If all the maximal square minors vanish, at that point the rank has to fall, and only at such points the rank will fall, and therefore that is a closed subset, okay. So this argument tells you that if you look at all the points P which are singular points, that is a closed subset of X, that will be a closed subset of X, okay. So the set of singular points is a closed subset, but the more important fact is that this closed subset is by no means the whole space, it can only be a proper closed subset, which means it will be of smaller dimension, and that needs proof, and I will prove it in the next lecture.